This is an introduction to Laplace transforms. And the first thing to realize, to know, is this is very different than everything that we've done to this point in this class. But it is a worthwhile thing to learn. I'm not an engineer, but I know in talking to engineers, especially electrical engineers, use Laplace transforms a lot. What is a Laplace transform? Use a cursive L here. It is an example of a linear operator. What does that mean? It's a linear transformation. Linear operator is just another name for linear transformation, though a linear transformation in certain special circumstances, typically linear operators are like derivative operators. They take functions as input and give you functions as output. Just like a derivative does, right? You plug in a function into the derivative ddx operator, say, ddx of f of x, you get f prime of x, a new function out. This is something you should be used to somewhat, right? Maybe it takes a long time to really get used to it. For a given function, the book uses a little y of t here. I could have used a little f of t. The Laplace transform of y of t is a function, is another function. And it's traditional to call its variable s. And somewhat traditional to write an of s right there, which is really weird notation. This is somewhat traditional. L of y of t is a function of new variable called s. What does s represent? It doesn't really represent anything. We just need a letter other than t and y and L. S, close to t. S is the chosen letter, okay? So this is going to be a function of a new variable s. And how do you figure out what function it is? You do an integral. And it's not just any old integral, it's an improper integral from 0 to infinity. You integrate y of t times e to the negative s times t dt. You heard of Fourier transforms? Laplace transforms and Fourier transforms are related to each other. Laplace transforms are a little easier. There's really no good way to do Fourier transforms, in my mind, without dealing with complex numbers. We can deal with Laplace transforms without talking about complex numbers. This is a function of s, because you're integrating the t away. It goes away, right? Integrate with respect to t, there's no more t's. When you do the integral, you treat the s as a constant. But it's an arbitrary constant, so in the end, the answer depends on s, and so you can think of it as a function of s. Again, the letter s is just arbitrary. It's just what is chosen. All right, well, what's that for? It's for solving differential equations. That's what it's for. But let's do an example calculation of a Laplace transform first. The best example to start with is to let y of t be e to the at, where a is constant. And by the way, the s, yes, I put it there, but we typically don't bother putting it there. So I will not write an of s here, though the answer will depend on s. Typically don't bother because it's just too cumbersome. So according to this definition, I need to do this integral. A, by the way, is a constant. A is constant. All right. It's an improper integral. Does it even converge? You can combine the exponents like this, right? That's a property of exponents. We also could factor out a t. And maybe it's even better to factor out a negative t, because if we do so like this, that puts us in a symbolic situation where we're imagining maybe maybe S minus A is a positive quantity, so negative of S minus A is a negative quantity, and that's going to make this integral converge if that's true. Right? Improper integral from 0 to infinity of an exponential decay will converge, from Calc 2. If that exponent of t, that multiplier of t was positive, it would not converge. It's exponential growth. And if S equaled A, so that this was 0, it would be e to the 0, which is 1. That's not going to converge either. Yeah, I want S minus A to be positive, so negative of S minus A is negative. And this is equivalent to saying S is greater than A. Is that worthwhile to even mention? Yeah, I think it's worthwhile to mention. Does it affect anything? Not much, other than just getting the answer. It's going to be the domain on which the Laplace transform is defined, the domain of S values. Maybe you're good enough at integrals, you can just do this in your head. I think I've practiced enough. Oh, and should I go ahead and play an engineer today? Right, the mathematician would say, hey, you can't write that. You should, and you can't write the final answer without putting a limit sign in there. Okay, really? Because improper integrals are really limits of proper integrals. But I'm going to play the engineer today and pretend infinity is a number. And pretend I can plug in infinity here. Or should I even write an infinity in place of t? Oh, my mathematician friends would be mad at me. And that's 0, right? E to the power is never ever 0. Well, except if the power is minus infinity. E to a numerical power is never ever 0, including all possible complex numbers. But an engineer would say, plug in a minus infinity, and e to the minus infinity is 0. So this is 0, and looks like the answer, this is a 1 here. Looks like the answer is 1 over S minus A. For S greater than A, so that the improper integral really does converge, and this all makes sense. All right, the Laplace transform of e to the AT, a function of t, is this function of S. Who cares? We're out of time. What you should care about is that this is useful for solving differential equations. The very first section, it's going to feel like, of chapter 6, it's going to feel like, well, why are we bothering? Because it's just a harder way of solving differential equations I already know how to solve. That's what the first section of chapter 6 is going to feel like. But once you get to the second and third sections of chapter 6, which will stop after the third section, you are all of a sudden at situations that you can't solve any other way. So even though the method feels harder and weird and unnatural, it is very useful for certain circumstances.